Apart from admixtures, we have cement, water, and aggregates in a concrete mix. So far, we have discussed about cement and water. Now we are going to discuss about aggregates. Aggregate is the material in granular form. 60 to 80% in volume in a Portland cement concrete is aggregate. So it is important to learn about aggregates because the concrete properties are depending on aggregate properties. One of the reasons for using aggregates in a concrete mix is to reduce the cost. Because aggregate makes up to 60 to 80% of the concrete volume, their properties strongly influence the properties of fresh and hardened concrete. To produce quality concrete, each aggregate particle must be completely coated with the cement paste, and the cement paste must fill all void spaces between aggregate particles. The amount of cement paste that we needed in a concrete mix is depending on the particle size distribution of the aggregates and also the particle shapes. We will discuss these things later on. Aggregate must be strong, resistant to freeze and thawing, chemically stable, and free from fine materials that would affect the bonding of the cement paste to the aggregates. Aggregate properties are depending on the aggregate source. Aggregate sources can be natural or they can be manufactured. Natural sources of aggregates are the rock quarries, river run deposits, and the gravel pits. Rock quarries can be inorganic rocks, sedimentary rocks, or metamorphic rocks. River run deposits are natural sands and gravels. Gravel pits are the natural gravels that we can find in the environment. Manufactured sources can be slag waste from iron and steel mills. Most of the aggregates that we use in the construction industry are natural aggregates. They take thousands of years to form, and also we can't control the properties when they are forming because they are naturally forming. So it is very important to test the aggregates before we use to find whether they are okay with a particular construction. Now we are going to look at these properties of aggregates. As we mentioned earlier, aggregates are natural materials, so they can be industry byproducts, and its engineering properties are depending on the rock mineralogy, structure, grain size, texture, and the degree of weathering. Also, aggregate properties have a significant impact on structural and functional performance of a structure. So it is important to learn about the properties of aggregates. We are going to look at 5 important properties of aggregates: particle size distribution, we call it the grading, durability, moisture content, bulk density and the particle density, and the specific gravity. Let's start with the gradation or the particle size distribution. Gradation helps determine almost every important property in a concrete mix. The allowable aggregate gradation is specified for any application depending on the project requirements. In some situations, available aggregates in the market need to be blended to achieve the allowable aggregate gradation for a specific project. You can see some examples here. The first picture shows single size, that means uniformly graded. You can see just one size of aggregates. In the second picture, you can see poorly graded. In this example, you have only 2 sizes. Well graded has different sizes, so the small particles can be fill the gaps between the large particles, so you can see the aggregate mix is densely packed. There are some advantages of having well graded aggregates. It increases the stability, it reduces the water infiltration, and it reduces the amount of binder needed. However, minimum void space is needed to provide adequate volume for the binder, so the well graded is not specified in every application. Let's see how to evaluate the particle size distribution of aggregate lot. We can do the sieve analysis to find the gradation of the aggregate lot. We are using a set of sieves with different mesh sizes, larger meshes at the top and reducing the mesh size when you go to the bottom. And we can use a sample of the aggregate and we pour it to the first sieve, and we use a sieve shaker and we shake it for about 5 minutes. Then we find the amount of aggregates remaining in each of these sieves. We weigh it and we can find the mass retained in every sieve. We can use this data to plot the gradation curve. Let's see how we can do it. As we mentioned earlier, sieve analysis data can be used to plot the gradation curve for a particular aggregate lot. So the sieve analysis data that we get are shown in the table. So we have the sieve sizes and also we have the mass retained in each sieve. The gradation curve is the curve that we can plot in this graph. So in the y-axis you can see the percentage passing, and the x-axis is the sieve sizes. So you can see different sieve sizes here as you see in the table, and we need to find the percentage passing. The data that we get from the sieve analysis are not the percentage passing, we get the mass retained in each sieve. Now let's see how we can convert this mass retained to percentage passing. So to find this, first we need to find the total amount of aggregates that we used. So for that, we are adding this mass retained in each of the sieve. We are adding all this data and we can find the total mass. So that will be, when you add all these numbers, you will get 500 grams. So that is the total amount of aggregates that we used. Now then we need to find the percentage mass retained. So we use 500. Out of the 500, only 0 retained, so nothing retained. So 0 divided by 500 times 100% will give you the percentage mass retained. So in this one it will be 0%. And in the second sieve, which is 13.2 millimeter, we have 3 grams retaining in that sieve. So that percentage mass retained will be 3 divided by 500 times 100%. So this will be 0.6. Similarly, the third one will be 12 divided by 500 times 100%, and this will be 2.4. And if you proceed in the same way, you get 6% here, 8.6 here, 25 here, 36.6, 18, 2, and 0.8. So these are the percentage mass retained in each of the sieve. Now we need to find the percentage passing. To find that, what we do is we use 500 grams, nothing retained in the first sieve, that is 100% passed. So this will be 100. So how we calculate it is 100 minus whatever we have here, that is 0. So this is 100%. When you go to the next sieve, the amount passed will be, the percentage passed will be 100 minus both of this. That will be 100 minus 0.6 minus 0. So 0.6, this will be 99.4%. When you go to the next one, that will be 100 minus all 3 of these. The easy way to do that is you use the previous value. 99.4 minus 2.4. So our answer will be 97%. Then the next one will be 97 minus 6, which is 91%. 91 minus 8.6, it is 82.4. 82.4 minus 25 is 57.4. 57.4 minus 36.6 will be 20.8. 20.8 minus 18 is 2.8. 2.8 minus 2 will be 0.8. 0.8 minus 0.8 will be 0%. So you can see it will be the percentage passing is starting from 100 and it is going to 0%. So we have percentage passing here, which is the y-axis of our curve, and we have the sieve sizes in this column, and that is our x-axis. So if we have x-axis data and the y-axis data, we can plot the curve in this gradation graph. You have an example or else a question in the tutorial. You can try it by yourself now and you can plot the graph. Let's see to plot few points here. So 19 is here. 100%. So that will be the point over here. 13.2 is this one, and we have 99.4, so somewhere here. 4.75 is this one, and we have 97% for that. So this is 90, 95, So 97 is somewhere here. So likewise, you can plot all points and you will get a graph like this. So depending on the shape of the graph, we can determine what kind of a gradation that we have. You can see all the calculations and the graph here. Now let's look at how we can determine the type of gradation just by looking at the gradation graph. We'll start with the well graded or the densely graded. Where in the densely graded aggregates, we have particles in different sizes. So if I draw the particle sizes, we have particles in all of these sizes. So if you look at the graph, you can see the graph going throughout the graph paper. So you can see the blue graph, which refers to the well-graded distribution. And if you look at the description here, well-graded refers to a gradation that aggregates with a wide range of particle sizes. The small particles fit in between the large aggregates. Well-graded aggregates compact easily and leaves few air voids. Compacted aggregates tends to be dense and impermeable. Now if you look at the gap graded, you have a gap in the particle sizes. If you take these two sizes away, we get a gap gradation. In the curve here, the gap gradation is the green curve. So you can see a flat horizontal line at the middle. That means you don't have particles remaining in some sieves. The percentage passing doesn't change for that range. So that gives us the gap gradation. If you look at the description here, gap graded refers to a gradation that contains only a small percentage of aggregate particles in the middle size range. The curve is flat in the mid size range. Now let's look at the open graded. In the open graded, if you look at the particle sizes, we have the middle size particles, but we don't have the small particles. So then we get the open graded. When you look at the curves, the purple curve refers to the open graded. In this curve, you can see a vertical line at the middle size here, and also you can see a flat curve at the beginning because you don't have smaller sizes. So if you see the description here, open graded refers to a gradation that contains only a small percentage of aggregate particles in the small range. This results in more air void because there are not enough small particles to fill in the void between the large particles. The curve is nearly vertical in the mid size range and flat and near zero in the small size range. Now let's look at the uniformly graded. In the uniformly graded, you only have maybe one size. So the curve here in the graph is the red curve, which is this one. So if you see the description, uniformly graded refers to a gradation that contains most of the particles in a very narrow size range, that is, all the particles are the same size. We can summarize the particle size distribution in different gradations like this. If you look at the dense or the well graded, we have all the particle sizes. In gap grade, we don't have the middle size particles. In open grade, we don't have smaller size particles. And in uniformly graded, we have all the particles in the same size. Now we know how to identify the gradation type just by looking at the gradation curve. In different applications, we have to use different gradations depending on the project requirements. In some situations, we may not be able to find the required gradation in the market. In that situation, we have to blend available aggregate gradations to get the required gradation. Let's look at some terminologies related to particle size. According to the size, we can categorize aggregates into three groups: coarse aggregates, fine aggregates, and fillers. Sizes higher than 4.75 mils, we categorize them as coarse aggregate. Sizes in between 0.075 to 4.75 mils, we categorize them as the fine aggregates, and sizes less than 0.075, we categorize them as the filler. And there are other three important terminologies that we are using: maximum size of aggregates, nominal maximum size of aggregate, and finest modulus of aggregates. Now let's see what are they. Maximum size is the smallest sieve through which 100% of aggregates pass. Nominal maximum aggregate size is the largest sieve that retains 0 to 10% of aggregates. Finest modulus is a measure of the fine aggregates gradation by adding the cumulative percentage aggregate retained on each of the standard sieves divided by 100 gives us the finest modulus. The larger the finest modulus, the coarse is the aggregates. We are going to do a small example to see how to find the finest modulus. As we discussed, finest modulus is the sum of the cumulative percentage mass retained divided by 100. In this question, we have the sieve sizes and we have the mass retained in each sieve for this particular aggregate sample. So we need to find the percentage mass retained. They have given us the mass retained. We need to find the percentage mass retained. To find the percentage mass retained, we first need to find the total amount of the aggregate sample that we used for the sieve analysis. So when we add all of this retaining amount, we get the total amount that we have used. So when you add all that, you get 483 grams. To find the percentage retained in the first sieve, so it has 12 grams retaining. So 12 you divide it by the total mass, 483 times by 100%, you get the percentage mass retained, which is 2.48. In the second one, you do the same thing, but here 30 grams are retaining. So 30 divided by 483 times 100% gives you the percentage mass retained in the second sieve. That will be 6.28. Similarly, you can calculate the percentage mass retained in every sieve. So this will be 8.90. This will be 25.88. This is 37.89. This one is 18.63. Now we need to find the cumulative value of that. So we already found the percentage mass retained. Now let's find the cumulative value. So the cumulative value will be, you just add them. So when you go to the second one, that will be 2.48 plus 6.21, which is 8.69. When you go to the next sieve, you add another 8.9. So 8.69 plus another 8.9. So that will be 17.59. Next one will be 17.59 plus 25.88. That is equals to 81.36. Next one is 81.36 plus 37.89. That one is, I think this is not 81. This one is the 81. And this is 43.47. Then we have 43.47 plus 37.89 is 81.38. 81.38 plus 18.63 is 99.99. Now we have found the cumulative percentage mass retained in each sieve. Now let's find the sum of that. So that means we add them. So let's find the sum. When you find the sum, you just add these highlighted values. So I got 253.58. So this is the sum of the cumulative percentage mass retained. We need to divide that by 100 to find the finest modulus. So the finest modulus of this particular aggregate sample is 2.53. So these are the steps that we have to use to find the finest modulus. Here you can see the steps and the solution. Particle shape and texture are also important properties which determines the properties of fresh and hardened concrete. The shape and phase texture of the individual aggregate particles determine how the material will pack into a dense configuration and also the mobility of the stones within a mix. There are two considerations in the shape of materials, namely angularity and the flakiness. You can see the angularity and the flakiness of different types of aggregates here. The second aggregate property that we are going to look at is the durability. Durability is the ability of aggregates to withstand weathering and retain their dimensions and the mechanical property. There are four mechanical properties here we are looking at: strength, hardness, toughness, and the soundness. Strength is the ability to withstand applied loads in service. Hardness is the ability to withstand abrasion by other materials. Toughness is the ability to withstand impact loadings. And soundness is the ability to withstand the effect of moisture and temperature changes. Aggregates should be physically durable and also chemically durable. Under the physical durability, we consider the soundness and the wear resistance. Under the chemical durability, we look at the alkali aggregate reaction. The failure due to the expansion caused by the chemical reaction between the alkali contained in cement paste and the certain reactive forms of silica in aggregate, we call that the alkali aggregate reaction. Moisture content is another important property of aggregates because depending on the water that we have in the aggregates, we have to decide how much water we need to add for the hydration process. There are four conditions: oven dry, air dry, saturated surface dry, and wet. In the oven dry condition, we don't have water in the permeable voids. But in the air dry condition, we have some water trapped in the permeable voids but not up to the surface. In the surface saturated dry condition, we have water in the permeable voids up to the surface, but the surface is dry. But in the wet condition, we have water all around the aggregate surface. Let's see these four moisture conditions in more details. Oven dry condition is obtained by keeping the aggregates in an oven at a temperature of 110 degrees Celsius. This is long enough to drive all water out from internal pores and hence reach the constant weight. Air dried condition is obtained by keeping the aggregates at ambient temperature and humidity. Under such condition, pores inside of aggregates are partially filled with water. When aggregates are in either oven dried condition or air dried condition, it will absorb water during the concrete mixing process until the internal pores are fully filled with water. That means the water inside the pores are not contributing to the hydration process. In saturated surface dry condition, the pores of aggregates are fully filled with water and surface is dry. This condition can be obtained by immersing coarse aggregates in water for 24 hours followed by drying of the surface with wet cloth. When aggregate is under surface saturated dry condition, it will neither absorb water nor give out water during the mixing process. Hence, it is balanced condition and is used as the standard index for concrete mix design condition. In the wet condition, pores of aggregates are fully filled with water and the surface of the aggregate has a film of water. When aggregate is in the wet condition, it will give out water to the concrete mix during the mixing process. Since sand is usually obtained from rivers, it is usually in the wet condition. Now let's see how to calculate the moisture content. As we have four different moisture conditions, we can calculate the moisture content in different ways. We'll start with the oven dried condition. Moisture content in oven dried condition can be calculated using this equation. We can find the amount of water in aggregates by minusing the oven dried weight from the stock weight of the aggregates, and we divide that by the oven dried weight of aggregates and we times by the 100% to find the moisture content as a percentage. Moisture content for surface saturated dry condition also calculated in the same way, but here instead of using the oven dried weight of aggregates, we are using surface saturated dry weight of aggregates. Absorption capacity tells us how much water can be absorbed by the aggregates. We can use this equation to find the absorption capacity. Surface saturated dry weight minus the oven dried weight divided by the oven dried weight times 100% gives us the absorption capacity. Absorption capacity of an aggregate is defined as the total amount of water that can be taken by aggregates from oven dried condition to surface saturated dry condition. In design, a concrete mix, the moisture content usually use the saturated surface dry condition as the reference because it is an equilibrium condition at which the aggregate will neither absorb nor give up water to the paste. If the surface saturated dry moisture content value is positive, it means that the aggregate is under the surface moisture condition. If it is negative, it means that the pores in the aggregates are only partially filled with water. Now let's look at the bulk density and particle density. Aggregate weight is most often expressed on the volume basis rather than the particle basis. The bulk density is defined as the dry weight of aggregates divided by the volume. When you consider the volume, we need to consider the volume of aggregates and also the volume of space. So like this. So the bulk density is depending on how densely the aggregates are packed. That means the particle size distribution of the aggregates and also the shape of the particles. Specific gravity or the relative density of an aggregate is the ratio of weight to the weight of equivalent volume of water. That means the weight of aggregates divided by the weight of water. Aggregate specific gravity is needed to determine weight to volume relationships and to calculate the various volume related quantities such as voids in mineral aggregates and voids filled by asphalt. The specific gravity test measures aggregate weight under three different sample conditions because we have different moisture conditions. So weight of aggregates can be oven dried condition or surface saturated dry condition or submerged in water condition. So let's see how we can calculate this. There are four types of bulk specific gravities that can be calculated depending on which mass and volume that we consider. Apparent bulk specific gravity can be calculated by using the oven dried aggregate particles as the mass and the volume of aggregate particles as the volume. Oven dried bulk specific gravity can be calculated when we consider the oven dried aggregate particles as the mass and the volume of aggregate plus the volume of water permeable voids as the volume. Saturated surface dry bulk specific gravity can be calculated by considering the surface saturated dry mass as the mass and the volume of aggregate plus the water permeable voids as the volume. And effective bulk specific gravity can be calculated when we consider the oven dried aggregate mass as the mass and the aggregate volume plus the volume permeable voids volume minusing the voids that can absorb binder as the volume. In this slide, you can see a summary of the four types of the bulk specific gravities, and you can calculate the different types using these formulas. We are finishing the aggregate part with this slide, and we are moving to the chemical admixtures.